Hello, everybody. Welcome to the session. As people are hopefully finding their way to the lecture hall, I have also some questions for you. So this is a talk about flexible and efficient multiphysics simulations with the coupling library preCICE. This is very relevant to OpenFOAM. And before we start, I would like to ask you to use the poll feature here in the conference platform and answer a simple question about how familiar you are with preCICE. At the same time, I would like that you write in the chat now and throughout the talk what you would like to do with this. What fields would you like to, what multiphysics simulations would you like to do? Would you like to do fluid structure interaction, conjugate heat transfer? Do you want to couple nuclear fusion plasma? Do you want to couple helicopters, fish swimming, or what? And I think I just started the chat, the poll. I see already somebody wants to couple interFOAM and calculix. This is something that I think has been done. And someone says, I would like to simulate fluid structure interaction problems for thin solids. Yes, depending on how thin and strong the interaction, this is probably doable. All right, and I see now we have already 17 votes, and most of you have heard something about this, but nobody seems to have actually used it. So that's perfect, because we will take it from the basics. And I think we already have some matching here, as people found similar simulations they're working on. That's great. So, my name is Gerasimus Kurtakis. Many of you may know me as Makis in the community. Somebody asks about the slides. There is a handouts session, a handouts tab in the conference platform that links you to GitHub. And there you can click, even start the presentation to watch with me. OpenFOAM with DL2 for FSI, we will see today. Okay, so now I leave the chat aside for a moment. The people working around this are, of course, it's an important part of the project. The people we are developing this library at the Technical University of Munich and the University of Stuttgart. Main people here are in three groups. I come from the group of Professor Bunkerts at the SCCS. I work very closely with everybody, and specifically with Benjamin Neckermann, who now started his own chair at the University of Stuttgart. And of course, we have, since older, the group of Miriam Sulte, also in Stuttgart. And what is this library? What does it do? You have heard something about this. You've seen this picture before. We have a solver such as OpenFOAM that can do, for example, CFD, and we have another solver, for example, calculix DL2, that does structure simulations. And this could also be anything else. It could also be a particle solver. It could be your own in-house solver that we know nothing about. And these are some examples of codes we currently couple, and you can find these adapters that let you directly use the code with preCICE on GitHub. Today we will see OpenFOAM and DL2, but you can try all these different things. And in gray, I have some things that are probably coming soon. People are working on them. We will have, hopefully, Julia bindings in the future, in the near future. And there are some people already coupling particle solvers that want to share them with the community. What does this job, this box in the middle do? It takes care that the solvers can communicate, they can exchange values on their meshes, and they can iteratively couple the interface in different schemes, and also with acceleration methods such as interface quasi-Newton. And we are also working on time interpolation apart from space interpolation. Now, what will this tutorial teach you? First of all, how to couple two very simple toy solvers. The solvers will be written in Python, and it will be very easy to understand what's going on. Then we will couple OpenFOAM with OpenFOAM for conjugate heat transfer, and then we will couple OpenFOAM with DL2 to do some FSI simulation. In the first part, we will directly call the preCICE API as if you were trying to couple your own code. And in the parts 2 and 3, we will use directly the adapters, and everything I will show you, you will be able to already find online. Just a disclaimer in case people happen to watch my talk last year, this is going to be essentially the same, very similar, just with updates, for example, with a new structure in our tutorials and some scripts and configs, and some news at the end about the latest state of all of our resources. On the organizational side, I don't expect you to try things live. It will be a bit quick, but please use the chat, ask questions. You cannot really interrupt me, I just now realized, but I will try to pick some questions at specific points. You can find the slides on GitHub and follow with me. Everything I will show you is free software. You can just find it on GitHub and use it already. And since making partition simulations means bringing together multiple software packages, we have also created a virtual machine that you can just run, and it has everything already installed. Of course, you are normally supposed to run such simulations on a larger workstation, on a supercomputer, or whatever. Okay, now let's start with the two simple solvers. The dependencies we will need, the ingredients we will need for this recipe will be preCICE version 2. Currently, we are at version 2.2.1. And we have packages for Ubuntu you can just download, or you can get it from SPAC, you can get it from the Arch Linux user repository, you can get it especially for any Linux system. It also works on Mac OS, and Windows support is eventually coming. You will need Python 3. You will need two simple packages, NumPy and Matplotlib, for our toy code. And you will need the preCICE Python bindings that are very easy to install, like this. Our concept for this problem is very simple and not necessarily physical at all. We have a 1D code, a one-dimensional code, which we call a generator. And this is essentially a fancy boundary condition code. It is just, it just generates an array of random data, which we then introduce on the right side of this square domain, which we call a propagator. You can already see that the data that are injected here are convected and also diffused over time. So you can imagine that this could be a simple fluid-fluid coupling where you have two different fluid models, for example. Now, what are we going to do? We are going to do a unidirectional coupling. This is the simplest thing possible. What does this mean? We will be running our generator, and it will be generating some data. We'll be sending them via preCICE to propagator, but will not wait for any values back. This is the simplest thing possible, and would be applicable, for example, when you couple a near field acoustics with a far field acoustics field. And we will be sending every time step. How does this toy solver look like? As you see, it fits on this slide with large letters. First of all, we import our dependency, NumPy. We generate an array, a grid from 0 to 1 with 21 points. We set a time step size, we initialize our time to 0, and infinitely, or essentially until we reach our end time, we generate random data, which we will assign to a variable named u, to an array named u. And we want then that we couple this code with the other one. What does the other one do? It is a bit more complicated, of course, but still almost fits in a slide. It does the same thing. It has a 2D grid. It initializes everything with zeros. And right now in the uncoupled case, it sets a fixed value on the boundary. It prints a message propagating data and then applies this completely arbitrary convection diffusion rule. Let's see now what is going on here. If I just run my code with Python generator.py, it generates data and exits. This is an uncoupled code. Then I do the same with my propagator. And it also pops up a matplotlib window, and you see that propagates data and the data just diffuses. Note here that in this uncoupled simulation, we have this constant boundary. We have not yet coupled this boundary. It's not an interface. It's just constant values. Let's now gradually try to introduce preCICE. preCICE is a library for in C++, but it also supports other languages such as Python, C, Fortran, MATLAB, and hopefully soon Julia. So first of all, we need to import preCICE, the preCICE Python bindings in our code. We do this by adding this import preCICE statement. Then we need to configure preCICE. We need to tell it that, hey, you have multiple codes you need to couple, and I am the generator. Then preCICE needs to know all these coupling, mapping, communication options. All these are in this preCICE.config.xml file. So we need to tell preCICE where to find this file. In the structure we have at the moment, this file is in the parent directory. As preCICE is designed intrinsically for parallel simulations, for massively parallel ones even, it expects some MPI size and rank, which we here set arbitrarily to 0 and 1. Not arbitrarily, for a serial case with hardcode. Then we need to create the object we will be using to couple. And we name this interface. We call the constructor where we give these values. Now we still need to define the coupling mesh. So what are we actually going to couple? We're going to couple this small fillet on the right, if you remember, and we will name this generator mesh. And this mesh, this name is not arbitrary. It is defined in this configuration file that I will show you later. To be more flexible, we get a number, an ID that we use whenever we need to refer to a mesh. So our generator mesh will be mesh number 42, whatever. Then this is the mesh of preCICE, but we need to associate some nodes of our code with this interface. So we just iterate over our mesh, and we get the vertices on the interface, and then set them to preCICE with this set mesh vertices command. Of course, we have a question here: how am I gonna remember which arguments to use here, and so on? I will show you later that there is very detailed documentation, and in Python you can always just type help and then in parentheses the set mesh vertices, for example, and you get the detailed documentation of the method. Okay, after we have set the mesh and we have associated with some vertices, we need to initialize our interface. This tells preCICE, okay, now find the other solver and make some first handshake, and essentially in a parallel case also set who exchanges data with whom. After we initialize, we can start solving, and we will do more things here. And similarly to initializing, we need to finalize at the end. Kind of like Mpi, only this does more things. Now, in this time loop that we have essentially solved some equation. We have some new data. Now that we have new data, we need to essentially give them to preCICE and then tell the simulation, okay, I got new data, and advance. Advance meaning go to the next time step. Here I don't show you yet how to give the data and read new data, but you can already imagine how this is gonna go. We complete the time step, and we need to move on, and we need to iterate now, not until one of the solvers just wants, but we need somebody to decide about the global end time of the simulation. And this we delegate to preCICE. So we replace our previous while condition with while interface is coupling ongoing. So both or all the solvers, because we can have more, will run for as long as preCICE says so. At the same time, after advancing the time, preCICE will tell us what is the maximum time step that we are allowed to do in the next iteration, in the next time step. Because the two sides can run on different time steps. This is one of the advantages of the partitioned approach, that the time stepping of every participant is completely its own business. But eventually we need to synchronize to be able to exchange data at the right point. In the future, with time interpolation, we would not even have this requirement. So we need to restrict our time step size, and we need to get this value also since the initialization. So far, so good. Remember, what do we have? We have an object preCICE and we are now steering the simulation. We are essentially ping-ponging between solvers. Let's see what is the state right now. Of course, you need to do similar changes in the propagator, exactly the same. We started as before, and you see now that the one side starts and waits for the other. And it tells I'm the generator and I'm setting up my communication. The moment the propagator starts, the propagator waits for new data and then continues. And then you see that the generator has actually completed earlier than the propagator because we had this unidirectional coupling. And as you see, even though there was this synchronization and ping pong, nothing actually happened. So our propagator is still getting the same constant boundary. And of course, because we actually have not yet associated, we have not given these new values we computed to preCICE. So what do we do here? We need to give values to these vertices for specific data. We can have on every boundary, we can have multiple kinds of data. We can have at the same time temperature and forces, for example. And we can be reading from the same interface displacements. This is something we need in FSI. So here we will select a very arbitrary name data, and we could also name it color if you prefer. And similar to the mesh, we get a number, an ID for this data that we can refer to again and again. And after we compute a new solution, remember here we have created some random data. We write a block, an array of scalar data. So multiple numbers next to each other for temperatures. And if I had, for example, forces, this would be right block vector data. And I associate here, I write this data ID, this is color, on the mesh, generator mesh, on these vertices, actually. And what do I write? I write the solution U. And I do this before I advance. Advance tells preCICE, okay, now do your magic, mapping, communication, iterations, and so on. At the end of the advance, when it returns, we would have some new values to read. And we don't do this here because we have a unidirectional coupling, but you can imagine that this is what you need to put then in your propagator. We read the block scalar data. There is a question already by Hossein. Is this process for the first example the same for when we couple OpenFOAM with, let's say, Calculix? On the programmer's side, yes, it is the same. For the user, we have a shortcut so that you don't need to write all this code. But the principles I show you here are the same. So now it should work. Let's see what happens. We, again, go into the two directories. Could be anywhere in our system. We start the generator, it waits, and then we go to our propagator, we start it, and we see now that they exchange data. And you can notice here that we have these 3 steps that the values stay the same, and after 3 steps, they couple again, they change the color. And you see that the generator has already completed, but the propagator still consumes the buffered values that preCICE is still feeding it with in every iteration. So far, so good. This would continue for a while. And this is, again, the case we saw. So this is the most basic thing you can do. These are toy solvers with no physical meaning. It is a unidirectional coupling. It is serial, meaning that we have this staggered approach, first the generator, then the propagator, then the generator, then the propagator, even though at the moment the generator does not need to wait for anything new, so it just continues. Then we could also have parallel. So you could imagine you have OpenFOAM and Calculix, and instead of having OpenFOAM, compute forces give them to Calculix, and then OpenFOAM waits for new displacements, that they do a Jacobi style, that they exchange values, they compute their solutions, they exchange values, they compute the solution, and so on. And for those that probably joined a bit later, at the moment, I have only used Python. OpenFOAM comes in the next slide. And this was an explicit coupling, meaning that we only send data once, and maybe also receive once, but we do not iterate. If we wanted to iterate, we would be using an implicit coupling, and we could also accelerate it with Aitken, quasi-Newton, or something else. Also, here we had the same meshes essentially on the boundary, so we just used a nearest neighbor mapping. That's the simplest thing possible. But we can also, when we have very non-conforming meshes, we can do some more advanced interpolation, such as nearest projection or something based on radial basis functions. Very interesting question. Can this coupling be used for coupling OpenFOAM and mesh generator SnappyHex to update the mesh during the simulation? This would be a bit more elaborate, because you would need to again associate new vertices with preCICE. However, as a concept works, it would be a bit expensive, but of course, if you are to start a complete mesh generator, then this would probably not be the expensive part. I already know of somebody that, as a hobby project, mostly used it to couple a solver with a visualization tool to have a live visualization. You can do many things like that. Okay, I take a sip of water, and I think there are no more urgent questions. All right. As a side note, I would like to clarify some terminology, because people refer to these concepts with different names. What you just saw, that the one solver was essentially, so the propagator was propagating the same value for 3 steps before it receives a new set of values. And this means that the generator and the propagator essentially can do any time step sizes they want. And we call this, in our terminology, subcycling. I know that some other people use subcycling for what we call implicit coupling. Just keep this in mind. And for us, implicit coupling means that after you do one exchange of values, you check the convergence and move back to the previous time and redo it with new values. All right. Here is the configuration file essentially we used in a graphical description. And you can visualize this with a handy tool we have here called config visualizer. So what did we have? We had a generator code, a propagator code, and we had our Python script writing data to a mesh which was called generator mesh. At the same time, the propagator was reading this propagator mesh, was reading data from it. And we had an exchange of data. We had this generator mesh being sent to the propagator. And then from this copy, propagator was mapping values to its propagator mesh. This will become important in a moment. And you see here that the two solvers communicate in this case with TCP sockets, could also be with MPI. And we had a serial explicit scheme with the first participant being generator, the second being the propagator. How does this mesh look like? We have this config file. It is an XML file, meaning that looks a bit like HTML, but with our own tags. And first we define how many axes this interface has. And we say that our solvers are essentially exchanging 2D data. If I had a velocity, I would only have a horizontal and a vertical component. Then we defined the color, the data that we were exchanging, and the two meshes, the generator mesh and the propagator mesh, and they use this data, this color. Then we define two participants. The generator, as we saw already, defines this generator mesh and then writes data on it, which then propagator needs to consume. So what does the propagator do? It has a copy of this generator mesh from the generator, and it also has its own mesh, propagator mesh, which it provides, and then does this nearest neighbor mapping we saw, and it is consistent, meaning that just take the same value, don't do any integration, and it reads data from this mesh. We defined that we have an exchange using TCP sockets from generator to propagator, and as I said, now this could already be MPI. The only thing that the two completely separated solvers need to know is a file where they can write their address, so their telephone number, where can I call you? And usually we set this to be a directory where they both have access to. There's nothing else going on in this directory. Then we have the coupling scheme, which in this case we said it's a serial explicit. So we had the order that first will be the generator, then the propagator. And we had the coupling time window size. We call this time window to separate it from the solver time step. This was a bit confusing in the past. And we say that we will be coupling every 0.01 seconds. And we will do this until both solvers reach the maximum time of 0.1. Remember that we had the two solvers, and okay, the one was doing the mapping, but we needed to also exchange data, exchange a mesh. And this we define here. We say we exchange data, the color, over the generator mesh. So we take the generator mesh and we send it from the generator to the propagator. And yeah, that's the first look into the XML file, which we will discuss later again for OpenFOAM. Just for those that join later, you can find the slides in the handout section on GitHub and then follow with me. Now, you're here not because you want to couple some Python solvers for toy problems, but you want to do some multiphysics with OpenFOAM. So, for OpenFOAM, by the way, I'm sorry for some issues here. I realized that something is wrong with the phones. Okay, Now, what does an adapter do? An adapter is something we provide you so that you don't have to write all this additional code. For this simple toy solver, it was kind of trivial, but for OpenFOAM, and especially if you want to make something general, this is a bit more elaborate. So we give you a function object. You may be familiar with the concept. You may have used it to compute something at post-processing, for example. We give you a function object, a plugin that you just define in your control dict. This is an additional shared library that OpenFOAM links to at runtime. So you don't need to recompile OpenFOAM or anything, and it essentially works with a wide range of OpenFOAM versions. We really try to have this. And this adapter will be then the thing that will talk to preCICE. For your simulations, this is very easy. I will show you what it means. So an adapter needs to take new values from preCICE and apply them on the right places on the boundary. For example, on the face centers, on the face nodes of width field, and so on. And similarly, it needs to extract values potentially by computing some gradient or some flux, and then pass them to preCICE. It also needs to be able to set a time step, as we saw, and it also needs to be able to reiterate, to do this implicit coupling. So it needs to be able to redo an iteration. We accomplish this with checkpointing and with resetting the time. So it is a bit hacky, but it works. And as I said, adapt the time size. I have a bit of trouble following which question is the newest. Okay, I found a way. And Patrick asks, is there any coupling with FMI, FMU to couple with Modelica? Not at the moment. We don't develop something like this, but you may want to do this. Now, Hossein asks, theoretically, can any OpenFOAM solver be coupled with another tool using preCICE, or the OpenFOAM solver must be couplable? For example, having a moving mesh capability. This is a bit more complicated to answer. For the common cases of fluid structure interaction, for example, you just need to have mesh motion. If not, you need to also handle this, extend the adapter to also handle this additional motion in the way you do it in your special solver. But for the normal OpenFOAM solvers, it just works. Could it be used with any version of foam extend? Unfortunately, no. At the moment, not straightforwardly, because we are using this function objects, and last time I checked, which is a while ago, this was not synchronized with the latest state of OpenFOAM. We already try to support both the OpenCFT and the foundation versions, but the foam extend code is significantly different. Philip asks, how difficult would it be to compile preCICE on macOS? It's very easy now. So we also have it in our continuous integration, and we know that it works. We have a documentation page that I can hopefully remember to reply here later. Okay, so here we will need preCICE again, a recent version of OpenFOAM, and the OpenFOAM preCICE adapter. Some news here, we finally put some things into shape and decided to release a version 1.0, which we will follow then, which we will continue with semantic versioning. We have releases, and please download a release for your OpenFOAM version. For OpenFOAM 8, we are going to release something. The code is getting significantly different. We're trying to put everything into a compatible shape. But there is a branch you can try already. And then you need to build it, and you do this the same way you compile OpenFOAM with OWMake. So this is very common. It just essentially runs make and links it to preCICE. There is nothing really fancy going on here. If you have heard of this in the past, there used to be additional dependencies about YAML and so on. We don't have this anymore. It's much more simplified. Now, we are going to run one of the tutorials together for conjugate heat transfer. And you will say, but I want fluid structure interaction. And yes, this is coming. But let's start with this because it is simpler. So what do we have here? We have a channel flow, and we have a thick plate under it, which we simulate with Laplacian foam. In this thick plate, we have heating. So we have a hotter bottom than we have the inlet actually of the channel. And the channel we simulate with buoyant pimple foam. And you see that the temperature essentially is convected with fluid, crosses the interface. At the interface, we have essentially some smooth transition. And we simulate this here for 10 seconds. You can find this tutorial with details on the documentation that I will show you also later. And what do we need here? We need two participants. On the one side, we will have OpenFOAM, and something is going wrong with this figure. It will be also OpenFOAM on the other side. And we have these two adapters configured via their own OpenFOAM dictionary. In the middle, we will have the OpenFOAM, the preCICE configuration file, which is shared by both instances. Now, if you download the tutorial, you will see that it contains several files. These are many more than you need because you see here we have a case named fluid OpenFOAM, which looks familiar to you. It has this 0 directory with velocity, temperature, and so on, a constant system directory, and here we have this preCICE dict. We also have a preCICE configuration file on the top level. And here you see we have all these different solid cases. So on the title of my presentation, there is something about flexibility. And this is because the moment I start OpenFOAM, I don't even need to have decided what to couple on the other side. I can start it, and then I can leave it waiting for 2 weeks until I develop a new solid solver or something like that. And then I can also start it, and provided that they are looking at the same address, they will just find each other and start coupling. Other solvers we have to try with this tutorial are Phoenix, which is a finite elements framework. Maybe many of you know this. And Nutils, that is another finite elements framework developed in the Netherlands, mainly. And we have here some additional scripts, for example, to clean all the cases, to clean this case, or to just run the solver This is not anything special or important. We mainly provide it here for convenience and for our system tests and continuous integration. So this will just run block mesh and buoyant pimple foam. Now, what we will focus on here will be the zero directory, where we will need to set compatible boundary conditions. We will touch the control dict, where we will need to point OpenFOAM to our function object, and we will add this preCICE dictionary. For the solid, similarly, we will again touch the zero and control dict and preCICE dict. The simplest one, I told you this is a function object, so we just go to our control dict on both sides, and we just add this part, similarly to defining a forces function object or something else. We say that I name this preCICE adapter or however, and this has the type, this, and you can find it there. So by default, this builds into your user big bin of OpenFOAM. That was straightforward. Then the adapter configuration. First of all, what is this? Why do we need it? We already defined this preCICE config XML. There we defined how the mapping looks like, how the coupling scheme looks like, and how the communication looks like, what is the data exchange, and so on. But OpenFOAM, at the moment, does not know what to do with the values that it gets from preCICE. And it also needs to tell preCICE which solver it is. So we provide this additional file that states, okay, here you can find the preCICE config. Remember that the solver starts preCICE. It's not that preCICE starts the solver. So OpenFOAM needs to tell preCICE where to look. And it tells you, okay, I'm the fluid participant, or I'm the solid participant. The OpenFOAM adapter supports different kinds of simulations. And at the moment, we require that you specify this to enable disable features, mainly to not have conflicts and to be able to extend it more easily. And here we enable the conjugate heat transfer module. And then we define our interfaces. We will have only one interface on top of the plate, at the bottom of the channel. We name it arbitrarily interface 1. And we associate it with the fluid mesh that preCICE knows. And then we associate this fluid mesh that preCICE knows with the interface patch that OpenFOAM knows. So we have named it like this in our block mesh dict. Then we need to tell OpenFOAM what kind of data it is actually exchanging, because what it gets from preCICE are essentially only some text. It does not mean anything for OpenFOAM. And we say that we will be reading heat flux in the fluid, and we will be writing temperature. And as you see on the other side, they are the reverse. So the plate has a temperature boundary condition at the bottom, computes a heat flux at the top, gives this heat flux to OpenFOAM, to the fluid, and then the fluid gives back a temperature, which then the solid reads as a new boundary condition. To be able to write either a value or a grade or a heat flux, we need to make sure that in our temperature, we have already specified a compatible type. So if we want to read the gradient, remember the fluid reads the gradient from the solid, we need to say that the interface has type fixed gradient, and the value here, the gradient, does not really matter. And on the solid, we need to tell it that, okay, I'm setting a temperature, so this needs to be of type fixed value. This is only for technical reasons, but you see there is no fancy boundary condition here. And there is a very good question, okay, why not make the whole adapter as a boundary condition? Yes, this could be an alternative good approach, but this could be less portable. And we try to support as many versions as possible, and we have found this to be a good enough approach already, because you don't need to recompile your solver or anything else. Okay, now the preCICE config we are using for this case. We are setting this problem to be a 2D problem. I can see already a potential question here, but OpenFOAM is 3D. How do I treat it as a 2D solver? Our problem is essentially 2D. We don't really have any Z direction. We define in the adapter automatically when you want to couple only a line of the interface, so to treat it as a 2D solver, we only take the face centers, for example. And this is important because we have other 2D solvers, for example, DL2 or Phoenix or Nutils or else, that we want to be able to couple also with OpenFOAM easily. So we have this additional automation in the adapter. Now, the data this time has more interesting names. It is temperature and heat flux. And the meshes are called now fluid mesh and solid mesh and associate with this data. There are questions that I will treat later. There is a question now by Andre. By defining it as a 2D, does it integrate, does it disregard the Z direction it gets? If so, what happens if your problem is defined in the XZ or YZ plane? Very good question. For the automatic 2D mode to work, we assume at the moment that a specific direction is the off plane, in this case, the Z. But I can also see in the future that we could make this configurable, though it is probably easier for the user to just rotate the case. Then we define the two participants. The one is called fluid, the other is called solid. The fluid uses this, provides this fluid mesh, has a copy of the solid mesh, reads heat flux, write temperature on the same fluid mesh, and it maps from its copy of solid mesh to the fluid mesh, again with consistent. Consistent is for things like temperature. Conservative mapping would be for things like force, where you need to make sure that the total force over the area is conserved. Now we also have the solid that does essentially the reverse thing, and it does everything on the solid mesh. It also defines a mapping where it maps from the copy of the fluid mesh to the solid mesh. Why do we need two mappings and two mesh exchanges in this case? It doesn't need to be that both solvers, both participants do it, but we need two, and we need two because we have now a bidirectional coupling. Similarly, we define the communication, and now we define a serial implicit coupling. Serial again means that we have the a first solver that is the fluid, and the second solver that is the solid. We have a maximum time of 1 in this case, different than what I showed you in the nice picture where everything has evolved, and the coupling time step size, coupling time window size. We will do this now iteratively. This is what the implicit means for us. And the first one will be the fluid, the second the solid, and the exchange will be happening sending the fluid mesh from the fluid to solid, and sending the solid mesh from the solid to fluid. This will iterate until the two sides of the interface tell the same truth, so until there is convergence, and we say that we want a relative convergence on the temperature on the fluid mesh to be less than 10 to the minus 5. Now you can imagine that this iteration takes a long time. Why not just use a monolithic coupling and so on? Okay, there are many arguments for using the monolithic or the partitioned in any case, but the performance is not really one, because we have methods to accelerate it, to accelerate the partitioned coupling iterations, so that you only need, for example, 2-3 iterations, or potentially even one if you are in a steady state. So we have different methods, and here we configure, for example, the Aitken under relaxation. This is an adaptive under relaxation that you may have heard of, and it starts with an initial constant relaxation of 0.5. And we accelerate the data on the second solver always, in this case, on the solid with a solid mesh. And we try to adapt the values of the heat flux on the boundary. So we get new values on the boundary that will probably give us faster convergence to the next. So all this thing I showed you in this text file was maybe a bit hazy, and this is easier to follow. We have our plate. It writes heat flux on the solid mesh. It sends a copy to the fluid. The fluid does a nearest neighbor mapping to the fluid mesh, from which it reads heat flux. Then it writes temperature to, again, the fluid mesh. It sends a copy to the solid. From this copy, we go to the solid mesh, and at the end, we get new temperatures. I see longer questions that I need to come to later for time reasons. But I see some nice suggestions for the implementation also. I would be very interested to follow up on that. Okay, now let's run it. I have here this demo virtual machine I told you about, where you can find also all the tutorials and all the adapters we currently have on GitHub and officially support. You can find them here. And this is also easy because you can just do whatever you want without breaking your system. Of course, it will be very slow. Okay, now, for the sake of the presentation, I will go and, for example, change the maximum time to something smaller so that the solvers complete faster. And I just go to my OpenFOAM case, and will also show you that I have enabled the adapter. And at the same time, let's also make it write a bit faster, a bit more results. And we start our case completely normally. For convenience, we could use this run sh script, but instead we can just do the normal procedure. We do a block mesh, and then we start the solver. In this case, buoyant pimple foam, it starts. It says I'm fluid. I'm trying to couple with the other solver, and the other solver does not exist yet. So we go and we also start our Laplacian foam. And you see that the two sides communicate. It is not really apparent because of the screen output, of course, but normally you would see that the one solver waits for the other in every iteration because we are using a serial coupling scheme. Quickly, somebody asks if this can be done also via Mpi. Yes, it can be done via Mpi. OpenFOAM can also run in parallel. And we have also performance-related papers and test cases, for example, on SuperMOOC in Munich or on HOC in Stuttgart, so supercomputers that you may also have access to. So I have now run it for the complete 1 second, and let's load both cases in ParaView. By the way, I recently found out that you can actually have auto-apply in ParaView. That is a life-saving. It is this little button on the top. So we get both cases, we group them together, and you see that the two meshes are completely different. There is, yeah, okay, the geometry is conforming, but the meshes are different. Let's visualize the temperature. And you see that it looks like as if this was solved by one solver. Of course, this is only a demonstration case. For validation, you need to look closer, but we also look closer when we need to verify that this works correctly. Okay. Now, there is another question. If you couple OpenFOAM to Python for a parallel case, would you need as many Python threads as solver threads in OpenFOAM? Very good question. So Python is a specific example, but in general, you need, you can define whatever you want on its side. So you have a very expensive OpenFOAM fluid simulation on the one side, and you start it, I don't know, on 200 cores, whatever. And you have a very cheap FEM simulation, and you start it in 1 core. And you can even have it on a different computer, even. And in case of Python, you can do something similar. You can start multiple, you can start 1, and so on. Now, let's go to the mechanical fluid structure interaction. And hopefully, we will go fast enough to have time for questions at the end. We have many more tutorials you can find. And now we have them nicely documented on the website. Before, they used to be on GitHub wikis and so on. We did a very significant effort of putting everything together in the past months. And we have such a toy FSI case with a 1D solver, a 1D cube, elastic cube, both in C++ and Python. You can couple them arbitrarily. An elastic cube in 3D with OpenFOAM and Calculix. And we have this case that I just showed you, and you could exchange OpenFOAM with Phoenix or Nutils. And I will now show you an FSI case where we will have a perpendicular flap, and we will be able to solve this with any of these fluid solvers, with any of these solid solvers. We will specifically solve for OpenFOAM and DL2. This is a case that you may be already familiar with. This is perpendicular flap. This is a 2D case. It's not exactly the cantilever beam in 3D. And you see here that our OpenFOAM solver applies some mesh motion, and the cells get different shapes. And this displacement we want to feed from a solid solver that's not visualized here. And in this case, it will be DL2. DL2, if you don't know, is an FEM framework and the collection of examples also tailored for HPC. And we also support it, and we have an adapter with some tools and an example solver for structure simulation. And just get these packages, and the case you can find again in the tutorials repository. Now, in the OpenFOAM side, we will again modify the fields where we need to set something, and we need to set a velocity boundary condition. So there we go and apply a moving wall velocity. The value does not matter at the moment because we will override it. This is mostly technical. Similarly, we have a point displacement, and we go and set the displacement to be a fixed value so that we can actually set a value. For the mesh motion, we will use displacement Laplacian. And our preCICE dictionary looks very similar as before. I'm again the fluid, and I enable this time the FSI module. We define one interface, and we call it, we associate the patch flap, which we have defined somewhere in the block mesh dict, with fluid mesh of preCICE. We also define where are the values located that we receive. And in this case, in this 2D problem, we will be receiving values that are meant to be on the face center. So we will define our interface mesh to be on the face centers, and then we will do an internal handling of converting these displacements to either point displacement, cell displacement, the right places. We will be reading displacements from the solid, from DL2, and we will be writing forces. Similarly, the DL2 adapter in its own format, this is a common DL2 configuration format. We specify that this is just technical for our example. We have it to handle this kind of geometry. And here, again, we point to the same preCICE configuration file. We say that this is the solid participant, works on the solid mesh, and reads forces and writes displacements. It could also write stresses, for example, or something else. And this is just a matter of changing one option. I will not go into detail. Here, I'm confident that now you already understand the large part. We have a fluid participant, just different thing now that we are using a radial basis function-based mapping. This is more advanced because we have the mesh really changing shape during the simulation. We want to have an interpolation that takes into account more points, not only just the closest one. And in the solid participant, we do something similar. Notice here that in this case we have both mappings on the fluid. That's also possible. And usually you want to have the computation of the mapping on the solver that also has the more computational cores associated with it, because this is an expensive operation. And we also defined here a watch point, which we will use later, to get some insights into our mesh. We say that we will track the values of the flap of the tip over time. And in this case, we have a parallel implicit scheme, meaning that OpenFOAM and DL2 operate without waiting for each other, just synchronizing whenever they need to exchange some value. So Jacobi style. What else is interesting here is that we have an interface quasi-Newton acceleration. We have different kinds of it implemented, and they can take different preconditioners, different filters, and so on. This is something that can really define the speed in which you converge. And one can spend a lot of time trying to optimize this. I will come to the rest of the questions at the end, just for the sake of time. Again, I'm running the 2 cases. I have decreased the time already to finish earlier. And you see I can start any of these fluid solvers. I start my fluid OpenFOAM case. And I will just be running run.sh from now on, just for to make things easier. You see it starts, it waits. This is pimple foam. And we also select one of these solid solvers and we start it. You see again this parameters file. The 2 solvers find each other. And it's again a bidirectional coupling, and soon they complete. Note here another technicality due to the function object and the way errors are handled. Due to the function objects, we may get some empty files. We have not found any way to automatically delete them. We've contacted also the issue tracker. The workaround currently is to just delete them to not get this flickering in ParaView. And let's visualize our case. We have loaded here the OpenFOAM case, and we visualized cell displacement. You see now that the mesh is actually moving, and where you see red is the largest displacement of the cells. Now, you don't see the solid case yet here, but let's also load it. And these are just VTK files. Unfortunately, there's no easy way to synchronize them, I think. If you know something, I would be very interested. And you see also the DL2 files moving, having some stress values and so on. Of course, one can go into detail here. And instead of loading things in ParaView, a quick thing we can do is to just visualize this watch point with GNU-plot or any other plotting tool. And we see that it starts essentially, does a larger displacement, and then it starts finding some kind of steady state eventually. Not really shown here. And interesting is that very quickly you can just take this tutorial and run different cases and see how all this different combination of solvers and models underneath behave. And if you run everything, you will see, for example, that it is much better to support, to have higher order finite elements instead of just very stiff linear finite elements in calculus, because you see in calculus, for example, you get much different magnitude and frequency. Then in SU2, for example, you see that we are actually simulating here a compressible fluid, but in the example we have in these tutorials, OpenFOAM and Noodles use an incompressible fluid. So we're comparing a bit potatoes with apples here, but the message of this picture is that you can essentially, at runtime, just swap the components. So you have this flexibility. And at the same time, you can go from something as simple as your toy solver to a very performant OpenFOAM simulation on a large cluster, or maybe even some in-house code that can do even more. And if you're interested in hard numbers, you can also look at the tutorial we have on the Turecron FSI3 benchmark. And there you can also check the frequency, the magnitude, and so on with the reference. Now, some resources before we go into questions. First of all, this is our new website since December, January. And yeah, we worked hard to bring this together. It is on GitHub pages. Hopefully it is useful for you. I have also some, under these pictures, I have also some community activity numbers in case you're interested. And specifically for this one, we just started having some analytics that are privacy friendly, and yeah, we see these numbers. All the documentation is now on the website. It is sourced from different repositories next to the code. It has more than 100 pages at the moment, and most importantly, you have this button here to edit a page directly on GitHub. And this is a very easy way to contribute to this project. Again, everything is open source, everything is academic at the moment. So it is just fun to work on it. If you have any questions, we have different ways you can interact with us. One is in such workshops. And actually, the OpenFOAM community has played a very important role in driving this forward. Also because OpenFOAM is the most used fluid solver we have at the moment. And for 1.5 years now, we have this forum on Discourse, not Discord, Discourse. And this is a very popular platform also among other open source tools. It is free for community open source projects. It's really nice. It would be nice to see something like that also for OpenFOAM. I think there was some attempt there that maybe did not really find the audience it needed. If you need something more quick, for example, you want to contribute, but you don't know exactly how to run something or so, this is a very nice recent example. We have Gitter. This is not such a nice platform. It is a bit abandoned at the moment, but it will be integrated with Matrix. That is another very nice distributed chatting solution. Hopefully one day we will move to that properly. We have a YouTube channel. Hopefully you will find this talk also there in the future. Also talks from our workshops and some simulations we sometimes find people doing with preCICE. We add them in a playlist. If you want to just follow some news, maybe follow us on Twitter. We try to be active there every 1 to 3 weeks. If you prefer email and less dense communication, we started with a mailing list. We still run it, and we use it for announcements, a few per year. And we have preCICE workshops. We already did 2 We started in Munich just before the pandemic started. We were very lucky. Somebody before coming asked me, hey, I'm traveling from India, you know, and I was wondering, do you have any incidents there? Yeah, I say, you know, there have been 2 in the whole Bavaria. You know, maybe we were lucky enough to have it. It was great. We had 40 people. And this year, of course, we did it online, mostly organized by Stuttgart. And we had it on Big Blue Button. We had many more than these people shown here because we almost forgot to take a picture. And next week, if you are following the ECOMAS conferences, we are in the coupled problems. We have a mini symposium on Wednesday. Thank you very much to all these organizations and everybody we have collaborated with. This is free because partially of money of European taxpayers. And thank you also for contributing. This is my last slide. As a take home, maybe keep that this makes it easy to exchange your coupled solvers. You can just exchange DL2 with Calculix or whatever and try different methods while still having performance. I present this work, and usually I come to the OpenFOAM workshop as the closest to OpenFOAM in our group, but this is hard work of many more people. Once again, thanks a lot to Benjamin Nickerman and many more people. For the first time, I'm trying to also collect some personal feedback on how you like this talk. So please scan this and go to a very short form where you can give me some feedback on how you liked it. Thank you very much, and we have 7 minutes left for some questions. Let's see what I have missed already. I also asked in the beginning who would like to couple what. And it's not only fluid structure interaction, conjugate heat transfer. I just had a meeting today discussing a follow-up thesis. So this is already done, coupling 2 codes with preCICE for nuclear fusion, for example. This is really amazing. And you can find on our website more things that people are doing. Then the next question I have not addressed. So Henrik said the nice addition would be a set of derived boundary conditions that register themselves with the function object. This would be portable and get shipped with the preCICE adapter. This way, you do not need to specify paths names in the function object dictionary, and it's guaranteed that the boundary condition makes correct use of the data it gets. This sounds promising. I'm lacking a bit of time at the moment on this. It's not really my main project anymore. Then, thanks for your excellent presentation. May I ask if, okay, this was if we can use MPI. Yes, we can use MPI. Does it need the boundary patch on OpenFOAM model to be decomposed into one processor? No, you can have a decomposition across an interface. Is there any functionality for Mpi region coupling in addition to boundary patch coupling? So region coupling, I think you mean, for example, multiple cells, a cell region, or in our terminology, we call this volume coupling. People have done this, and they have done it for coupling, for example, porosity solver with OpenFOAM. They've done it to couple a heat source inside the fluid domain, and we are working in integrating a simplified perspective of this into the main adapter and our tutorials. The next thing I've not addressed is since the coupling example between the two Python solvers didn't use any dictionary files or YAML files, so no adapter configuration file, I wonder, is it necessary to define a YAML file or any other kind of file to build up the connection while writing adapters for in-house solvers in Fortran? It is necessary. If it is necessary, how to make it work with the adapter? So we call this an adapter configuration file because it just tells your adapter of whatever solver what to do with the data it gets, which patches to associate it with, and so on. You can hard code it in the solver, but of course then it would be not as user friendly, or at least if your user wants to do multiple things with it. The connection is essentially built with preCICE. This has nothing to do with these additional things. And if you want to do it in Fortran, then it's of course a good question what format to use and so on. I have no good answer there, but there are some classical formats you can use. If you don't have something particular in mind, YAML is a nice format. We just had we wanted to reduce the dependencies, and JSON is also a nice format that is easy to couple. By the way, I come from the Department of Informatics, so my interests are more in the software engineering, and I always hope to be able to collaborate with you on actually getting more physical applications. So what you guys are doing is amazing. Thank you very much as well. Joseph says, very impressive. Would you be interested to set up a tutorial for the tutorial collection at wiki-openfoam.com tutorials? Yes, that would be nice. And actually, we hope that with some collaboration, with some further testing, code cleanup, and so on, we can gradually pass over these adapters to the community and integrate them into the solvers themselves. We have already had discussions in the very initial state with Calculix, with SV2 once, and in DL2 we have done something similar. It would be very, very nice to at least make a connection there. Hossein asks, preCICE is applicable to both steady and unsteady problems, right? Right. So we also couple buoyant simple foam, for example, and its iteration is then your time step for preCICE. It doesn't really matter for preCICE. Anonymous says, thank you very much for being here. Olga Sem says, great work and presentation. Thank you very much. Andres says, I mean to add mathematical models for patient-specific hemodynamic pressure to CFT blood flow simulations as boundary conditions. This is a very active project, a very active research. People are doing it with different ways, and this is actually related also to what I'm doing in my PhD right now, where I want to couple solvers of completely disparate models and dimensions. So you could have, for example, this vein and a 3D heart or something like that. So let's talk later. I've missed some parts. Can they deal with big deformations? This mostly has to do with the mesh motion solver you use. Of course, with it also supports. You can also use overset grids to think in a bit different framework, but this mainly comes from the limitations of the ALE approach. Time is running out. Conservative mapping, yes, we have. Joseph, eventually we will come in touch. Thank you for being here. When simulating particles, I need to solve a stiff PDE. Yeah, let's talk later. Thank you very much. I don't know if the session is still running. In any case, thank you all very much for being here. Just in case the live recording is still, the live session is still up. Trying to solve stiffpd for its particles time. I intend to do it with Python. Do you think this works better with preCICE or with directly calling Python from OpenFOAM? Yeah, the best would be to discuss this on our forum. In the discussion forum, we already found two people that, one that wants to do FSI with Interfoam and another that's already doing it. Yeah, so thank you very much for being here. And now I have to leave you. See you later in the workshop. See you at the next workshop. See you at one of the preCICE workshops. Ciao, ciao.